What's going on, guys? So in this video I'm going to be breaking down everything you need to know on practical skills and uncertainties. This is for anyone who's taking A-level physics, so that means if you're in year 12 or year 13, this video is for you. So if you don't know who I am, my name is Mr. Ceeraz. I'm a qualified physics teacher with over 15 years teaching experience, and in my spare time I run my own YouTube channel, yes, Ceerazzledazzle Physics, which contains hundreds and hundreds of videos to help you with your academic studies in order to ensure that we can help as many kids get the highest grade possible in physics education, especially in the UK, because yes, it is a difficult subject. Everyone thinks it's easy. No, it is quite hard here. And this video is for anyone who's taking AQA Physics, Edexcel, OCR. It's all in one video. I have made every single resource myself. If you check out my website, we'll have additional resources to help you with your studies as well. But it's all in here so that you can watch it. And you can pause the video as we go along and make your own notes. Also, if you get stuck, obviously drop me a comment. As you can see in all my other hundreds and hundreds of videos, I respond to every single comment. I do my best to help as many kids as possible, and I hope you enjoy it. So let's do this. 3, 2, 1, bang. Let's do this. A-level physics, practical skills and uncertainties. Prefixes: tera, capital T, power times 10 to the power 12. Giga, capital G, times by 10 to the power of 9. Mega, capital M, times by 10 to the power of 6. Kilo, K, times 10 to the power of 3. Centi, lowercase c, times 10 to the minus 2. Milli, lowercase m, times 10 to the minus 3. Micro, the symbol mu, times 10 to the minus 6. Nano, lowercase n, times 10 to the minus 9. Pico, p, times 10 to the minus 12. My advice to memorize this is going to be look at the numbers. If you just look at kilo going upwards, it's 3, 6, 9, 12. And if you look at milli going downwards, it's minus 3, minus 6, minus 9, minus 12. It's only centi which ruins the symmetry, times 10 to the minus 2, but that's an easy way to memorize the prefixes. The SI base units, the International System of Units from the French System International d'Unités. Yeah, that's where the SI comes from, yes? Quantity, these are all the SI units that you need to know. Mass is going to be kilograms, length is going to be in meters, time in seconds, S, current in amperes, capital A, temperature in Kelvin, capital K, the amount of substance is the mole, the mole over here. Luminous intensity is going to be the candela, CD over here. Uncertainties now. So here is going to be a description of all the different terms that we use when talking about uncertainties. The uncertainty is the interval within which the true value can lie. It is given by a plus or minus value. For example, 20 degrees Celsius plus or minus 0.5 degrees Celsius. So the maximum it could be is 20.5 degrees Celsius, and the low it could be is 19.5 degrees Celsius, like a tolerance. The resolution is going to be the smallest interval of a measurement device. For example, a thermometer can measure to the nearest 1 degree Celsius, therefore the resolution is 1 degree Celsius. A 30 centimeter ruler can measure to the nearest millimeter, therefore the resolution is 1 millimeter. So basically it's the smallest measurement you can make on that device. Accuracy simply means how close your values are to the expected value. For example, if G is equal to 9.8 and you've got a value of 9.7, you're accurate because it's close to the expected value of 9.8. Precision means how close your values are to each other. So for example, let's say you obtain the values of 9.7, 9.8 and 9.9. Because they're all close to each other, yes, therefore your results are precise. It's nothing to do with accuracy. Repeatability is when you do the same experiment and you get the same results. Yes, or the same group of students do the same experiment and get the same results here. Reproducibility is not the same as repeatability. That's when similar results are obtained when different students using different methods do the experiment and get the same pattern or results. So reproducibility is about somebody else doing it. Repeatability is about when you do it. Zero error is going to be an error which occurs when the measuring instrument registers a value when it's meant to read 0. For example, a weighing scale that reads 10 grams when nothing is placed upon the balance. Yeah, so let's say you have a balance, nothing's on it, it weighs 10 grams, obviously that's an error. Or let's say you have a voltmeter not connected to anything and it reads 2.5 volts, that is also a 0 error. When it's meant to read 0, it's not reading 0, that's why it's called a 0 error. To obtain the true value, you would have to subtract or obviously add the 0 error to your readings or reset the measurement device if that's possible. An error is the difference between the measured result and the true value. Systematic error, a type of error which causes consistent differences between the true and measurement value. So a good example I always explain it via is going to be, let's say somebody's watch was 5 minutes ahead. Every time you ask them the time, it would always be 5 minutes ahead. So that error remains consistent each time, every time you've obviously asked them for the time. So in order to obtain the true value, you can subtract the systematic error from the value that you need. So let's say, for example, someone said it was 10 o'clock, but you know their watch is 5 minutes forward, therefore it's 9:55. Parallax error is going to be a type of error which occurs when you do not take the reading at eye level. This usually occurs when you have like a marker in front of a ruler. The reason why is because if you look at it head on, the marker is right in front of the ruler, but if you look at it from a weird angle, obviously it changes slightly. So that's going to be when you take a reading when it's not at eye level here. Another good example is going to be, imagine you had an analog clock. If you look at it head on right now, you can obviously both the hands look at a certain direction, but if you view it from a different angle, obviously it changes where about the time reading that you'd obtain. So that's going to be a parallax error. Uncertainties. The uncertainty is the interval within which the true value can lie. If one reading is taken using a measuring device instrument, the uncertainty is half the resolution of the instrument. And obviously the resolution, as we stated earlier, is going to be the smallest non-zero measurement that can be taken using the equipment or the interval. For example, the resolution of a classroom thermometer is 1 degree Celsius, okay? So if we were taking the temperature of the room and the reading is 20 degrees Celsius, we can say that the temperature of the room is 20 degrees plus or minus 0.5 degrees Celsius. So I've taken the 1 degree, I've divided it, this is 0.5 degrees Celsius. Example, another one. A block is placed upon a weighing scale and the scale reads 100.00 grams. The resolution of the weighing scale, what is the smallest thing it can measure? Well, it'd be 0.01. Yes, looking at that, 0.01. And therefore, we can say that the block has a mass of 100.00 plus or minus, don't forget I have to half it, 0.005 grams over here. Uncertainties. If multiple readings are taken using a measuring device, we need to calculate a mean, and the uncertainty is now not the resolution of the instrument. So if you take multiple readings, let's say for example the length of something, yes, at three different points, you don't look at the resolution. You have to take all your values into consideration when working out the uncertainty. The uncertainty is calculated by the range of measurements divided by 2. So we have to take the maximum value of your readings minus the minimum values divided by 2. And here's a worked example. The length of a cubic suite is measured 3 times using a 30 centimeters ruler. The values obtained were 24.1 centimeters, 24.3 and 23.9. As we have multiple values of the length, we need to calculate the mean first of all. So let's calculate the mean of this. So 24.1 plus 24.3 plus 23.9 divided by 3 gives us our mean of 24.1. The uncertainty is going to be your maximum value minus the minimum value divided by 2. So 24.3 minus 23.9 divided by 2, it's 0.2 centimeters. So therefore, I quote my value, 24.1, which is coming from the mean, plus the uncertainty now, which we calculated by max minus min over 2, plus or minus 0.2 centimeters. Why do we take one reading sometimes rather than multiple readings? Well, it depends on the experiment that we're looking at. Some measurements will not have a lot of variation, hence why we take the readings once. For example, if I put a block on a set of weighing scales, we only have to take the reading once, and there's only one way to put the block on the scales. Yes, it's not going to change that much if I change it around. The reason why we take multiple readings is due to the variation of that instrument, of that measurement. For example, if we take multiple readings of the length of a cuboid suite, as the suite will obviously have slight variation across it. That's the reason why we take multiple readings here. If we were to take our reaction time, we would also take multiple readings. The reason why is because there's going to be a lot of variation as well. But let's say, for example, we were to measure the temperature of a beaker as it cools. Yes, you'd only do it once because there wouldn't be that much variation as you take the reading off it. So it depends upon the readings that you're taking, whether or not you take one reading or you take multiple readings. Combining uncertainties. So how are we going to combine uncertainties? Right, so let's say, for example, we actually have the following. Yes, we are going to do Hooke's law experiment. We have a spring of original length L. We add some weight to it. It extends to a final length F. Right, let's say the original length L is 2 centimeters plus or minus 0.05 centimeters, and the final length F is going to be 5 centimeters plus or minus 0.05 centimeters as well. Don't forget, I've halved the resolution of the ruler, and that's why I've put them for both of them are going to be the same. Obviously, to calculate the extension, it will be the formula, the extension is equal to the final length minus the original length L. So 5 minus 2, it's 3 centimeters. But what would be the uncertainty? because the original length L has an uncertainty of 0.05, the final length has also 0.05. Right, so the rule is this. Whenever the formula is the addition or subtraction of quantities, you simply add the absolute uncertainties together. So I simply take this value and add this one to it to obtain the total uncertainty for my extension. So we know the value of the extension is 3 centimeters, but then if I take the 0.05 plus the 0.05 centimeters, it will be 0.1 centimeter. So therefore, look, my final value is 3 centimeters plus or minus 0.1 centimeter. Don't forget where that 0.1 comes from. I added them both together here because the formula was the addition or subtraction of quantities of the same units. So let's say obviously extension is equal to F minus L. Yes, it could be a formula, let's say X is equal to A plus B. Because the formula is an addition, yes, I do the same thing and add the absolute uncertainties as well. Now, thinking about this in a bit more detail, I thought I'd run you through this. So let's say you were to work at the maximum value of the extension could be, yes, the maximum value. Well, obviously it would be the upper value of F minus the lowest value of L. That would give me the largest value of the extension, 3.1 centimeters. If you do the maths, you'll recognize it would be 3.1. You can pause the video and have a look yourself. And let's say if you were to work at the minimum value of the extension, well, it would be the lowest value of F minus the highest value of L. Yes, and once you've done that, you realize it will be 2.9 centimeters. So look, you can clearly see that 3.1 centimeters and 2.9 centimeters, look, are both incorporated into our value. We said it already, 3 centimeters plus or minus 0.1 centimeter over here. So obviously that is the upper and lower bound of that value here. And that's why it works out for us. Combining uncertainties in a different example right now. So what happens when the formula, it has times and divide of different quantities? So let's say you're given this table. So I'm going to walk you through this. It's a bit difficult, but we'll walk you through the entire thing. Let's say you're given, you're trying to work out the density of a cube. You measure the mass once. Don't forget, you only do it once because it's not going to change when you put it on the balance in different orientations. But you measure the length of it at different times, yes, at different points, the width of it at different points, and the breadth of it at different points over here. To work out the density, it's equal to mass divided by volume, the mass divided by the length times by the width times by the base. As the formula has quantities which are multiplied and or divided together, so notice you can't add the absolute uncertainties now because look, you're timesing and dividing now, and they have different units. You can't do what we previously did. We simply cannot add the absolute uncertainties. Now we need to add their percentage uncertainties together. So we have a new term now, the percentage uncertainties. Right, so first of all, you need to work out the uncertainty value first, then we work out the percentage uncertainty. So don't forget, you have 3 readings, yes? If you have 1 reading, you defer to the resolution of the instrument, fair enough, but now we have 3 readings, we're going to use the max minus min divided by 2. So maximum value minus minimum value divided by 2 for each one of them. So first of all, let's do this. So here's my expanded table. So the mass, there we go, it's still the same. Now the length, don't forget, it was 8.6, 8.2, 8.4. Let's work at the mean of it. It's 8.04. If you were to work at the mean of this. The width, let's do that as well, 5.023. The breadth of it, 5.00. So we've got the mean of all of them. Yes, the length, the width, and the breadth over here. Now, the uncertainty, yes, oops, just ignore the fact that I haven't expanded this box. The uncertainty would be equal to, don't forget, your maximum value, yes, 8.06 minus 8.02 divided by 2. That's how I get the 0.02. And then for the width, it's 0.01. And for this one over here, because this is a nice little trick over here, if there is no range, like obviously there's no range here, you defer back to the resolution of the instrument here. So this is a proper worked example here. So therefore this becomes 0.05. Yes, don't forget, I half the resolution to become 0.05 here. So that's where we got, and obviously my mass, the uncertainty would be half the resolution over here, so 0.05. So now we have the uncertainties of the mass, the length, the width, and the breadth. Obviously, you have to use the range over 2 to work out the length and the width one over here. Now, working out their percentage uncertainties. Okay, so the table, I've now copied it from the previous slide, it's now over here. To work out the percentage uncertainty, you're simply going to be doing the following. You're going to take your uncertainty, divide it by the value times by the 100. Yes, obviously it's the uncertainty divided by your value times by 100. So here's my table of results. Let's walk you through how we work out the percentage uncertainty in all of them. The percentage uncertainty to the length is going to be equal to 0.02 divided by 8.04 times by 100, it is 0.25. Pause the video, make sure that you've actually got these calculations yourself. The percentage uncertainty in the width, 0.01 divided by 5.02 times by 100 is 0.2%. Next one, percentage uncertainty in the breadth is going to be 0.05 divided by 5 times by 100, it's 0.1%. Then the percentage uncertainty in the mass is 0.05 divided by 543.2 times by 100, it's 0.01% over here. And then finally, we can see that the total percentage uncertainty in the density is the percentage uncertainty in the mass plus the percentage uncertainty in the length plus the percentage uncertainty in the width plus the percentage uncertainty in the breadth. So I simply add these all together. So 0.25 plus 0.2 plus 0.1 plus 0.01 is going to be 0.56%. That is my percentage uncertainty in the density. We haven't worked out the density yet. Let's work at the density. Density is mass over volume, so it's the mass 543.2 divided by the mean of them. So we have obviously we go back to the mean of each one of them. The mean length, breadth, and width. 8.04 times by 5.02 times by 5. We're going to get 2.69 grams per centimeter cubed. Then finally, we can say that 2.69 plus or minus 0.56% grams per centimeter cubed. But don't forget that is the percentage uncertainty. You must convert back to the just absolute uncertainty. So you work out 0.56 of this, which will come up to 0.2 grams per centimeter cubed. So never leave your answer as with the value plus the percentage uncertainty. Work out the actual value it will be. So as you can see, it's 2.69 plus or minus 0.02 over here. Accuracy and precision explained in more detail. Right, so I've got 4 dartboards here to help explain the difference between accuracy and precision. So accurate results are results which are close to the expected value. Precise results are values which are close to each other. They're not the same thing, accuracy and precision. Please do not just throw them into an answer when you think it's right. Obviously, you make sure you understand what accurate means and precision. Right, okay, so first of all, let's say you did an experiment. You've got gravity, you know it should be 9.8. You've got 9.7, 9.8, 9.9, and 9.85. Well, obviously, they're all close to each other, yes, and they're all close to the expected value. These are both accurate and precise. Right, what about this one? So this one is going to be accurate but not precise. So let's say, for example, you've got gravity to be equal to 9.8. Well, you know it's going to be 9.8. You've got 10.4, 8.4, 7.5, 9.8. Right, so this one's are accurate results. They're close to the expected value, but they're not precise because they're not close to each other. This one's going to be not accurate and not precise because they are not close to each other at all, and they're not close to the actual value itself. Yes, it's meant to be. So let's say gravity was 9.8 and you got 15.2, 4.2, 20.4 and 2.4. They're not close to each other, nor is it close to the expected value. Not accurate but precise. This one's going to be, let's say you know gravity is 9.8, you got 4.5, 4.2, 4.3, 4.1. Notice they are all close to each other, so it's precise, but it is not accurate over here. Make sure you understand the difference between accuracy and precision. And that's it. That's the end of everything I know on practical skills and uncertainties all in one video. If you liked it or you found it interesting, make sure you bookmark it and drop me a comment if you don't understand anything. I'll do my best to solve all your queries. Tag someone who's struggling in physics as well. If you can, it helps keep my channel as active as possible. Take care, goodbye, and good luck. If you're looking for additional resources, including my own revision notes or academic tuition, get in contact via my website or drop me a comment.